Welcome to the analysis seminar. It's a great pleasure to have Ben Jaye from Georgia Tech and now from Bonn, who'll speak on multiscale analysis of Jordan curves. It's all yours.
Great. Well, thank you very much for the invitation to speak today, Jaye and Dima. It's a great pleasure to be speaking at your seminar. And so I'm going to talk about some joint work with Xavier at Tolsa and Michele Villa. And it regards the extent to which one can detect kind of regularity in a set through kind of multiscale analytic measurements associated to the set. So kind of the elevator pitch, if you want, for this kind of set of questions is the following type of question. So we have a well-known analytic principle that we can decompose a function into, say, wavelet coefficients, and knowing something about those wavelet coefficients can tell us something about the analytic behavior of the function associated to them. So is there an analog of this for sets, right? So this is kind of this is the general kind of question that we're asking here. And there were several motivations for introducing this kind of question, and the kind of motivations came from different areas of mathematics, right? So first of all, the study of harmonic measure on rough sets, for instance, in work by Bishop, Carleson, Garnett, and Jones. Removable sets of bounded analytic functions by Jones and David-Semmes, and then more recent work by Azam and Tolsa running with this theme. Work in the calculus of variations by, say, Reifenberg, and then leading a lot of work to more recent work by Neighbor and Valtorta. And then kind of somewhat related to the first set of problems in some sense, this area has found some nice applications in kind of manifold learning problems. Kind of a longer term project of Koifman is to understand how well this stuff fits into kind of statistical learning problems, and you can see this carried out in work of Chen and Lerner. And so yeah, there you're looking at these kind of, you have this set distributed in space, and you have these measurements that you're taking of the set, and you want to know to what extent does your set live on or near a lower dimensional surface. Okay, so that's kind of where that comes about. Okay, so that's kind of where the motivations for this area came. So what I'm going to talk about today actually primarily is a rather cute problem in the plane. So we're just going to be working in the plane today, and there's lots of work here that's kind of primarily, I guess, considered useful in higher dimensions, particularly, for instance, this work of David and Semmes, Azam, Tolsa, Neighbor, Valtorta, and Reifenberg, and Koifman, and Chen, and Lerner. You would consider this kind of higher dimensional theory, but today we're just going to be talking about a simple problem in the plane. Okay, so we're just going to talk about kind of a pretty simple analytic problem, which is when does a curve have a tangent point at a given point on the curve? Okay, so to be precise, let's just start with the definition of a tangent point. So what do I mean? I mean, if I take any angle here, say less than pi, right, then I have a line which we see here, and I have a radius. I can zoom in sufficiently far close, right, so that the cone with aperture centered with aperture theta and vertex x only intersects the curve gamma at the point x, right, and moreover, has the property that each of the cone components is in a different connected component of the curve. So. Okay, so that will be our definition of a tangent point. If you have any questions at any point, please do shout. So that's our definition of a curve. And we want to test when does a curve have a tangent point without explicit knowledge of the parameterization, okay? So here we're going to restrict our attention to Jordan curves, non-self-intersecting curves. So these are going to split the plane into two connected components, right? So if your kind of a priori opinion of what a Jordan curve is a curve that looks like the curve in the picture or like a polygon or something like that, then you might think, okay, so how unusual is it that a Jordan curve should have tangents or not? Maybe you would expect Jordan curves to have tangents. So I just want to show next kind of two typical types of behavior that a Jordan curve may have where you wouldn't have tangents, right? So the first example here is something that's very well known, right? So this is the von Koch snowflake on the left-hand side of the picture here, right? So this is formed of a self-similar construction, right? And this curve here is going to have Hausdorff dimension, I guess, log 4 over log 3. Okay, and this is not going to have a tangent at any point, right? So in fact, that the set of tangent points of a curve has to have sigma finite length, sigma finite h1 measure. And this self-similar construction, which has got a higher dimension, which has Hausdorff dimension greater than 1, this isn't going to have tangent points at any point in the set. Okay, but this is, regardless, it's the image of an injective Holder continuous map, right? So we can have Holder continuity with an exponent of, I guess, log 3 over log 4, right? In how we would parameterize this this curve, right? So we can have this kind of fractal snowflake constructions, right, where we wouldn't expect to have tangent points. And also we can have something appearing on the right. So what we have here is a Cantor set, right? So this would be constructed by taking a square as our like 0th generation, and then our first generation would be looking at the 4 squares inside, right? And then we would continue 4 squares of relative length 1/4, sorry, in the corners, and then we would repeat this construction again and again. And if you're looking at this, you're thinking that, well, that's absolutely not a curve, right? Because it for instance, it's disconnected, right? So it's completely not a curve at all, right? But actually the fact that it is so disconnected means it can be contained in a Jordan curve, right? So that this Cantor set here is totally disconnected, right? And a very classical theorem of Denjoy-Rees, which is often called the Denjoy-Rees theorem. My font's a little bit thick here, so let me see what I can do about that. Here we go. Is that every totally disconnected compact set can be contained in a Jordan curve, can be covered by a Jordan curve, right? So this is a result from the start of the 20th century, and essentially can be kind of done in a first analysis course, as long as well, it would be kind of a hard exercise, I guess, but it's for a student in a first year analysis course, but it doesn't require anything. It's just you kind of cover your set by blobs in a kind of similar way than you would in a Cantor set. Then you join the blobs together, and then within each blob you then cover the set by smaller blobs within each one, and then you do some local modification inside, right? And there you're kind of preserving the order of the blobs as you're going down, which ensures you have injectivity of your map ultimately. Okay. So every totally disconnected set can be contained in a Jordan curve, and moreover, of course, say as written here, I guess this Cantor set has Hausdorff dimension 1, right? But we can construct Cantor sets, totally disconnected sets in this way that have positive Lebesgue measure by just making the factors, the contraction factors get smaller and smaller as we go down in the correct rate. Right, and so in this way we can actually find Jordan curves whose image has positive Lebesgue measure, right? They can't be space filling, of course, because of kind of puncture connectivity issues, but they can have positive Lebesgue measure, right? So I just, by these two examples, so first of all, these obstructions will kind of appear when we come to talk about the mathematics a little more. But moreover, the kind of Jordan curve being nicely behaved in terms of tangents is sort of rare in some sense, to put based on, like, at least it's a special property in opposed to how bad they can behave. Okay. So Jordan curves can be very wide. Right. So now we come to what kind of a multiscale measurement should we have, right? So I noticed Christopher Bishop's in the audience, who's a big expert in this field, and this talk's kind of designed for the non-expert in some sense. So this is actually a suggestion which by no means was the first one. It's the one that we will arrive at in this paper, and then afterwards, when we state the result, we will go back and we will look at other such measurements and how they relate. Okay, but here's one suggestion of how one might look and see. Okay, so how can I tell if I have a Jordan curve or not without a tangent at a point of my Jordan curve without explicit knowledge of the parameterization, right? So I can take a point X and I can look at a circle of radius R, right? And I can think, okay, so I can draw these two arcs. So I have this green arc here and this red arc, right? And I can compare the differences of these two arcs between pi r, which would be the length of the semicircle. Okay, and divide the quotient by r, so it's kind of normalized in some sense. And then if x is a tangent point of our gamma, then as r tends to 0, the lengths of the red and the green arcs, so they should both converge to pi r. Okay, so as this circle gets closer and closer, so here we've moved in and zoomed in a little bit more, and our arcs are getting closer and closer to pi r at any tangent point, because I can make my aperture cone wider and wider, and the green arc and the red arcs have to at least contain the length of those of the part appearing in each of the cones. Okay, so at a tangent point, one expects these measurements to converge to what happens when you have just a flat line. Okay,
and the definition of Gauss curvature in curved spaces is looking at the higher terms in the Taylor expansion, but here so it's very unlikely you will have higher terms, right?
Yeah, exactly. So indeed the second order term here would give you your Gaussian curvature, right?
Okay.
Yeah, so exactly right. Yeah, and yeah, there's actually some kind of applied work in the literature about to what extent can you tell a curve up to rigid motions by looking at these measurements, and in those cases you kind of have to go to the Gauss curvature in order to be able to say anything. Okay. But yeah, so that's what we would see if in advance we had our nice curve, but remember we might have this self-similar fractal type construction. So how actually would we measure this really, right? So we could think of our curve as looking a bit like this gamma, but if you were to zoom in, it would look the same again, and zoom in, and it would essentially look the same again, and zoom in, and it would essentially look the same again in some sense. Right, as you're going in and seeing it at a finer and finer scale. And so you're not guaranteed to only have one of these arcs in each of our connected components, right? So in our picture here we have omega plus, right? And we have a choice of what do we have a choice of? We have this arc, and the longer arc as our perspective choices. So we just pick the longest arc in each of our of our open sets, omega plus and omega minus, which are the two connected components around our Jordan curve, and we look at the maximum of the deviation from either of them from pi. Okay, and we normalize the coefficient by r. Okay, so this is our coefficients epsilon xr. Okay, so that's what that's going to be. That will remind you of the definition, but that's what's going on. So you can think of them as those two arcs as before, but because you're not guaranteed only to have one arc in each of your components, you pick the longest one. Okay, and then so what have we seen? So we've seen at a tangent point x of gamma, this coefficient epsilon xr tends to 0 as r tends to 0. So what could maybe you would expect a converse statement to that, right? So maybe if epsilon xr tends to 0, then you would have a tangent point. But that's not true, and that was never suggested, to be clear. So here we have an example of, well, it's a few generations, but it would be a Jordan curve, which is it's kind of made out of adding semicircular arcs. It's done so in a way that the Hausdorff dimension of this set is going to be equal 1, but it's going to have infinite length. And this epsilon xr is going to converge to 0, but still I'm not going to have tangent points. I don't have locally finite Hausdorff measure anywhere on this set. So I need something more than just convergence to 0. Okay. You might say if I had small epsilon xr's, maybe I'm contained in, say, a Holder curve, right? And actually that's kind of what Weifenberg was doing. If we remember, I mentioned the reference on just the first slide. So he was kind of interested in curves or sets rather, which kind of are pretty close to a plane, right, as you go down. And it turns out that means you have to have a snowflake and you're contained in a Holder map. But for tangents, you need more than just this epsilon xr tending to 0 as r tends to 0, right? But there was no question of this actually being sufficient, and in fact much more was known. So there's this theorem which kind of appears in a paper of Bishop, Carleson, Garnett, and Jones, and also in Christopher Bishop's PhD thesis, that uses kind of earlier results of Berling in some sense, that say that except for a set of 0 length, so 0 Hausdorff measure, if gamma has a tangent at x, then we even have square summability of these coefficients. So we don't only have that they converge to 0, but we have square summability of them with respect to the invariant multiplicative measure dr over r. Okay, so we're going to call this script Ex. This is going to be called the Carleson square function from our perspective, and so we know that at tangent points we have this precise rate of behavior of this function, and then the question arose was to what extent could this condition be sufficient? So say you have a Jordan curve, and moreover you know that this is finite or this is finite, then does that give you tangent points modulo throwing out a set of 0 length, which is the natural kind of exceptional set in this problem? Okay, so this was kind of known as the Carleson epsilon squared conjecture, and I guess the first mention of it would actually be in Christopher Bishop's PhD thesis of 1985, but you can also find that in his very nice survey article on harmonic measure in 1990. It's also stated in a monograph of David Sams, a paper of Bishop and Jones, which I'm going to return back to in just a minute, and Garnett and Marshall's monograph on harmonic measure. You can find this paper stated so given the prior theorem, that the unknown direction of this was if you have that this square function is finite, then modulo a set of zero one-dimensional Hausdorff measure, does this tell you that you have tangents at every point? Okay, and a couple of years ago in 2019 with Jaye and Michele, we showed that this is indeed the case. Okay, so what I would like to do for the remainder of the talk is show how this result kind of, well, at least look at some prior results that very much were helpful in terms of this and have proved very important in this area, and then discuss the proof a little bit and the main components about how to prove such a result. So, but first of all, just to mention here that the kind of analogous results for functions, which are kind of quite a similar nature. So let's say that we have a real valued L2 function. This is a theorem of Stein and Zygmunt from 1964. Then up to a set of Lebesgue measures 0 on the line, we have a classical derivative for f at a point if and only if we have two assumptions. So first of all, that this second order difference is little o of t as t tends to 0, and secondly, this second order square function, right? So maybe it's a little easier to see if we divide by t squared here, right? So this kind of second order difference here is square integral dt over t. So there are very natural, very close looking versions of this result for functions as well, and very classical ones. Okay, so much of the theory around this work of multiscale analysis of sets and how it relates to regularity of the set is built upon a number introduced by Peter Jones called the beta number. So how does this work? So we look at the following quantity. So let's take it one step at a time, right? So if we first look at this final thing, so we would fix a line L, right? So this would be our line L in this case, right? And we look at the supremum over gamma at y and gamma intersect our ball x of radius r, okay? And we look at the distance from y to this line, right? So it's saying how wide a cylinder do we need? So how wide a strip do we need to enclose gamma intersect bxr around, or how big a neighborhood of the line L do we need to enclose gamma intersect bxr? Okay, and then we pick the optimal line for that. So we pick the best possible line, and then we scale it by r. So then we divide the quantity by r ultimately. So we have that this beta of gamma xr is less than some number beta if gamma intersected with bxr is contained in the beta r neighborhood of a line L. Okay, so it's about finding how wide a neighborhood do we need. And then there's a very nice theorem by Bishop and Jones who proved an analog of this Carleson question with the beta numbers. So except for an exceptional set of 0 length, so 0 Hausdorff measure, a Jordan curve gamma has a tangent at a point x if and only if the square function with the beta numbers is finite. Okay, yeah, so, and moreover, they prove a quantitative version of this. So if we have a set E of diameter less than or equal 1, and we know that the square function is uniformly finite, then E is contained in a curve, and we moreover can say what length the curve is. It's C times E to the Cn, right? And this is very natural in terms of what this should be, because if we think of say a certain number of generations of a snowflake construction, right? So our first might look like that, and then our second generation might look like this, and so on and so forth. And we're going down, down, down. We can, to collect a number m here, we can go down m generations of this construction, right? So to get a square summability there, we can go about m generations down on our snowflake construction, and doing so is going to build up a length which is exponential in m, right? So this is sharp. And we don't know whether there are kind of quantitative analogs of this for kind of these Carleson coefficients. Okay.
Ben?
Yep.
Ben? Hi. First of all, I'm not sure I can see the whole screen. I don't know if other people have the problem. There's something hidden at the bottom a little bit. But my other question was, you mentioned the Stein-Zygmunt theorem. So does this have to do with the fact that somehow the Zygmunt class measures the functions that are well approximated by lines? Is there a relation between these two results?
Yeah, I'd say so. Yeah, absolutely. Yeah, at least morally. I'm not sure how explicit the relationship is, but morally it's very close. Yeah, yeah, absolutely. Regarding the screen, I can see the whole thing here. So the screen finishes with this CE to the CM bit. So this is the last line of the screen here. So I think I can see the whole thing on my laptop. But yeah, if anyone's having an issue, then let me know.
I can see it, Chris.
Okay, cool.
I can see it, Dima.
Cool. So yeah, so that's yeah. So this is a very nice theorem, and moreover, it gives actually another proof of 1/2 of the direction of the Carleson conjecture, because these beta numbers. So if we were to compare the beta number and the Carleson coefficient, right? So typically the beta number is larger, except for certain cases. So if you were to have a curve and it has a nice tangent point, right? Then in circumstances like this, then the beta number and the Carleson coefficient are going to be at best comparable, and the beta number is often larger. But if the curve turns back on itself like this, then you can be fit in a small tube. So you're going to have very small beta number, but you're going to have a very large Carleson coefficient, right? It turns out that such radical turns back on yourselves don't happen so often, right? So, but yeah, it's not always true that the beta number is larger, okay? But it's kind of typically true in some sense, okay?
And if we have a surface in space, I suppose we can define something similar, right?
So this is actually one of the really great things about this beta number in particular, is that generalizes very easily to higher dimensional surfaces, and in particular, so the work of David and Sems, they did a lot of work on higher dimensional analogs of this, and there are higher dimensional analogs of the Bishop and Jones theorem, in some sense by Lerner from the early 2000s. And then kind of, I guess, unpublished work by Jones and Lerner. But yeah, so it kind of doesn't really see the topology so much of the underlying set. So absolutely, that this can be done in any dimension. Sometimes you want to kind of slightly change your norm. So sometimes you don't really want to look at a supremum here, but you want to kind of look at kind of a least squares analog. So you want to kind of integrate square with respect to some measure, or you want to look at some different kind of version. Yeah. So there's a large industry about higher dimensional analogs of this, and absolutely you If you want to, when you're looking at kind of higher dimensional surfaces, and you want to characterize smoothness of higher dimensional surfaces, looking at, instead of the supreme and looking at integral squared quantities, is somewhat more natural due to some kind of counter examples of what can happen in higher dimensions when looking at this supreme. This quantity turns out to sometimes be a bit too big in higher dimensions to really characterize smoothness. Okay. Cool. So that's, yeah. So this beta number will appear in our proof, and we will kind of look to kind of say something in terms of these beta numbers and kind of find a way to tie into this theory, this Bishop-Jones theory involving the beta numbers along the way to proving the result. Right. So in the remainder of my time, I kind of like to sketch the proof and yes, see how we do. Before I do, should I finish at? Is it a 50-minute seminar or a full hour?
I don't know, 55.
55, cool.
Yeah, we can always stay for
I don't like to run over, so I just wanted to make sure. So we'll make it 55, and 20 more minutes is perfect. So that'll do really nice. So let's recall our setup. So we have our curve gamma, and then we'll look at the largest two components. So this is gamma plus r and gamma minus r. That are in our ball, that are on a circle of radius r centered at a point of the curve, and then we look at the maximal defect from the length of a semicircle. Okay, so what we want to show is that except for an exceptional set of zero length, if this square function is finite, then gamma has a tangent at a point x, right? And the proof splits into two parts, and very broadly speaking, the two parts are to handle these two constructions. So two obstructions in some sense. So the first part of the proof, you can say very broadly, is trying to eliminate Cantor type structure within the set. And that kind of then, in some sense, reduces you to being in the class of snowflakes. And then the second part of the proof, in some sense, says it can't really be a self-similar snowflake. It has to kind of exhaust its length and really be a Lipschitz curve. Okay, so in some sense, this is what's going on. Of course, the result is local, right? So we're only really looking at this collection of points where the square function is finite. There can be other parts of the curve where it's infinite. So we should view all these things as just local statements. So we want to rule out this Cantor structure locally, and the same statement about the snowflakes again locally, right? And so one thing I should add before we get into it, and we'll see why it's useful to have this quantity in just a second, is although it's smaller, it's good to introduce a new quantity which is somewhat more stable than these epsilon Carleson coefficients. And we get that by just integrating over them with respect to, say, the Gaussian measure, right? So if we look at this quantity here, which we'll call alpha xr, what is this, right? So we look at, and we only have to look at one of the components, omega plus, because if it's small for omega plus, it's also small for omega minus. And what we do here is we compare pi over 2, which would be the integral of this quantity if we had a half space, and we compare that with the integral over omega plus. So you would get this by just integrating the semicircular estimate with respect to a Gaussian weight, right? And notice it's getting more and more concentrated, right? We have that r squared there, it's getting more and more concentrated. And so if we have information of the Carleson square function, we certainly have information of this square function associated with these smoother coefficients, but we'll see why we need those in just a second. right? So really the main part of the main novelties in the argument are in the first half of the argument in some sense. The second part, it's quite nice to explain, but it's kind of a variant on standard theory in some sense. The first part is a little bit less easy, I think, to explain, but it's where I think the kind of the majority of the newer concepts in the paper are. So what are we looking to do here? So informally, what we want to do is rule out Cantor subsets in the Jordan curve, and we're just looking for some indication of some degree of flatness. Okay, so this is going to be a kind of compactness argument, and it says that for every beta greater than 0 and theta greater than 0, there exists some delta such that the following holds, right? So that let gamma be a Jordan curve, mu be a one linear measure with one linear growth supported on gamma. So a measure is one linear if you look at the start, if the measure of any ball is at most its radius. This is kind of just a useful bookkeeping mechanism to relax to measures in some sense. So you really what we're interested in is a subset of positive length, a non-trivial subset of positive length. But when we're dealing with compactness arguments, it's useful to relax this to a setting of Borel measures. Okay, so actually we don't care if the set is on a higher dimensional set, right? If it wants to spread out and become higher dimensional, then so be it, right? And that's what this relaxation to measures enables you to have. So let's suppose we have a ball centered on gamma such that the measure of the ball is non-zero. It's at least something compared to its radius, and we're going to scale it in this way. Then if we have reasonable control over these coefficients in the sense that the epsilon coefficients and the smoothed out alpha coefficients, if we have this local behavior on their square functions in the way that the L2 norm with this, the norm with respect to d mu is at most delta times the measure, then the beta number here has to be small. Okay, so it's saying that if you have a finite Carleson square function and you zoom in and in and in and in as much as you can, then and you have a set of positive measure on which it is finite, then the curve must be getting flat. Right, it must be contained inside of a thin strip. Okay, so this by itself doesn't imply tangents for the same reason as we saw before. We can have this kind of flatter and flatter snowflake going on, but it gives you enough to kind of then appeal to kind of an argument of David and Sem's, which I'm going to recap after this. Right.
And so this integration against the Gaussian, sort of maybe in a very naive way, reminds of like Perelman's entropy, for which comes up in flows, you know, I don't know, Ricci flows or something. But I think for mean curvature flow there is something similar. So, but maybe I'm just being completely silly because just Gaussian appears in both, but there's no connection. But
So the use in it is that it's real analytic for us. It doesn't matter so much that it's Gaussian. So I would bet a lot of money that its use is somewhat more naive than in flow. So we'll see why it comes up in a minute. We'll need the fact that it's essentially a real analytic function that decays a lot at infinity. We're not going to use any heat equation. That there's no so the finer properties of it being a Gaussian are not so important for us here. Although actually, so a few properties of it being a Gaussian will be used, but you have some flexibility.
See, for the mean curvature on the plane, there is this, if the curve is smooth, there is a wonderful version of Grayson's theorem, right? That the curve flowing by the Gaussian curvature converges to a round circle. Can you, in some sense, define it for rough curves, which will, I don't know, in some weak sense or something, that will improve the regularity? But I have no idea whether this is true or not.
I've got nothing to say on top of my head, unfortunately, but it's an interesting thought. Yeah.
Anyway, so sorry for asking silly questions.
Yeah, it's an interesting idea. Cool. Yeah. So what I want to do is we're going to look at a compactness argument. So if this statement is false that we want to prove, then there exists some beta and some theta, because it was for every beta and every theta. And we have some sequence of Jordan curves, all containing some fixed point, say 0, and some sequence of measures, but the measures all have non-trivial mass in the unit ball. But this quantity is getting smaller and smaller and smaller. Okay, so this square function quantity is getting smaller and smaller and smaller, but these beta numbers here are getting divorced from 0, right? So what we want to do is essentially then say that gamma j converge to some well, it's just going to be a closed set gamma that's going to be kind of local in some Hausdorff metric, and these mu j's we can pass to some subsequence that converges weakly to some measure, at least its measure of the closure of the ball is going to be bounded from below, right? Such that some analog of this is going to be 0. So this quantity here with respect to the limiting objects, whatever it means, is going to be 0. And from that, we want to actually concur that the curve must be flat. So the curve must be a line segment there. And that would arrive as at a contradiction, right? So doing this, we want to arrive at a contradiction. And so let's kind of see what the obstacles are in a collection of toy problems, right? So the first most toy of toy problems would be, let's say our limit curve is indeed, let's say our sets omega j plus and minus converge to some sets omega plus minus, and gamma j converge to a nice curve, and everything's beautiful, right? So kind of your back of an envelope idea of why such a thing might be true, right? So then you would have your square functions converging to 0. So what would that mean? That would mean that for every x, let's even say that it's even on the whole curve, every x in gamma intersected with b and r between 0 and 3, there exist complementary semicircles. There exist semicircles C plus and C minus that are contained in omega plus and omega minus. And then we want to conclude that it's a line, right? And if we have smoothness, this is no problem at all, because we can take some point, say here, and say, okay, so let's suppose it has positive curvature, or let's suppose its curvature is not 0, say. And then we just immediately reach a contradiction, because one of the semicircles is going to be much smaller than pi, right? One of these semicircles, omega plus and omega minus, is going to be much smaller than pi. So this is a very, very toy problem, but it kind of illustrates that these kind of the epsilon going to 0, at least in some very naive circumstances, would give you flatness. Okay. So the thing is, of course, is that the limits of these Jordan curves, they don't have to converge to anything anywhere near as nice, right? And secondly, we only have information on a subset of positive measure, right? So let's deal with, for instance, that second issue first. So we only have this kind of complementary set, this epsilon condition being 0 on a set of positive measure. Right, and this is one place where these alpha numbers are useful. So there's a kind of a second version of a toy problem. So let's suppose that this is our limiting configuration of our gamma j's and the component sets. So we have that one of the things is omega plus is a non-empty open set. Omega minus is R2 minus omega plus, and gamma is the boundary of both. And we suppose further that we have Z, which is the nodal set of a real analytic function that's contained in gamma, and we have a subset with positive H1 measure, right? So this is really where we use the Gaussian structure of those alpha numbers, because we would have we would have this kind of pi over 2 minus 1 over r squared omega plus e to the minus x minus y squared over r squared, I guess, squared, dm2y. This is 0 for all r. You can integrate this over r, and it's a real analytic function of x. And so our z here can just be the 0 set of that function. And so our kind of set where we have these complementary semicircles is also contained in an analytic curve, right? Due to it being we have a non-trivial analytic. The nodal set's not the whole space, so it's going to be locally some finite union of nice curves. And this is going to enable us to pass from behavior on a positive subset, a set of positive measure, to the whole line. Okay, so doing this Gaussian thing, it's a useful bookkeeping device, getting the additional smoothness, and then we can like use an identity principle and say, okay, we have something in a subset of positive measure, that then we can move to saying something about being at all points. Okay. So that allows us to go from that condition to so that's where these alpha numbers are really kind of one of the places, at least, where they're really useful for us. But nevertheless, this setup here is also a bit too much to ask for. Right, so it's not so clear that we can assume that we're in the situation of this problem. So this would help us if we knew if we impose some additional regularity, scale invariant regularity assumption on our curve gamma. For instance, it was a quasi-circle or an NTA domain, or so basically that or this is weaker than an NTA domain, but there are balls of given radius that are inside the set and outside the set. In each of the components, we can find balls at any scale, right? Then we can pass to the limit and we can say we have this type of behavior. But in general, there are, of course, there are sequences of Jordan curves such that they kind of can be approximate space filling curves, right? They can approximate piano curves, like for instance this classical construction. So that the limit of our gamma j's might be the whole space, right? And then in that case, there's these kind of epsilon coefficients that we're looking at. They're actually not really telling us anything. The condition completely collapses to being vacuous. Right, so we just have no information at all. So what we really need to do is understand something in the pre-limit, right? And this is really the final step of the argument. So we need to understand what having these square functions says in the pre-limit will tell us about some topology of the sets that enable us to kind of carry out an analog of the previous version of the analysis. And this is the existence of corkscrew balls. So here's our set gamma, right? And what this is saying is if we can find 2 points, so this is x and this is x prime, right? And their distance is, let's say, exactly r. This isn't necessary to be exactly r, but why not? We can assume it due to just measure theory, because we have this set of positive measure. And we know, moreover, that we have reasonable control of our square function at the point at those 2 points. Then we can find balls in each of the components, omega plus and omega minus, say. Right, so what that enables us to do is say, okay, so we have some topological stability there, and that enables us to pass to the limit. And essentially say we're in the situation of this toy problem too. So then we can use the fact we're contained inside some non-degenerate analytic curve, and using a lot of measure theory tricks, we can essentially reduce ourselves to that very first naive idea of if there's a point of non-zero curvature, one of the semicircles are very disbalanced from pi. Okay. If they're very small, if I'm sufficiently small. Okay, so that's kind of what goes into, those are the components that go into that result. Okay, so it's all a little technical, so I wanted to show you it in these kind of these steps of increasing technicality of what's going on there.
Ben?
Right, so we have this we've kind of removed this kind of Cantor obstruction in a certain sense. So
Ale wants to ask a question.
Oh, sure.
Sorry, on the previous slide, the balls should be contained in the ball of radius R around X. Is that?
In this slide?
The B plus minus.
Yeah. So, oh yes. Sorry. Yeah. This is sorry. You're absolutely right. Of course, this is intersected with BXR. Absolutely. Cool. Yeah. We need to be that they need to be also close to the curve on a radius comparable to R as well, right? So yeah, absolutely. Thank you for the correction. Yeah, completely correct. Cool. So our second step is modifying an argument which is sometimes kind of called a geometric corona construction. And this is a scheme of kind of David and Semmes, and then later further modified by Leger, right? And so yeah, so what's the setup here? So it's not an easy thing to pull off technically, but it's kind of a well-known scheme within the area. And the statement of this second step is as follows. So we suppose that we have an open set and gamma is the boundary of that open set. And we're in the situation that we were before, right? So we have like, so let's say unit scale where the mass of our ball is at least 1/10, right? And we're in the position where we know that our set is flat whenever our measure has decent measure compared to its radius. So whenever we take a ball whose measure is comparable to its radius, we know that our curve there has to be flat. And lastly, we know that these alpha coefficients, so these square Gaussian coefficients, that these are small at every point. Then what's it say? So it says that if I can pick this theta small enough and beta small enough, then I can find a Lipschitz graph with slope at least 1/10, say, such that the measure of the graph is at least 1/2 the measure of the whole ball. So this is an analog of saying if you're a snowflake, you kind of have to run out of length at some point. You have to actually be a Lipschitz surface. You can't be you can't generate more length as far as you go. And actually the idea is very nice. So I know I'm 1 minute over, but if I could just take 1 more minute to just explain the idea in one minute. So the idea that so if you have this property too, that your set is flat whenever the measure has reasonable measure with this compared to its radius, you have to be looking a lot like a snowflake. And if you have a snowflake that has infinite length, it actually has to rotate a lot on small scales, right? So the best line that's going to have, so the best line here is like this line. But then if I look closer here, the best lines are going to have very, very large slope. Okay, so the slope of these best approximating lines that are contained in this beta definition, they have to be rotating a lot. Okay, so, but then again, there's a mechanism that prevents the rotation. And this is the following kind of Fourier transform argument. Right, so let's suppose that gamma is the graph of a compactly supported Lipschitz function, and we let U plus be, say, the region above gamma. So it's the set of Y2 above our Lipschitz graph. Then we can control the Sobolev norm of A, so the integral of the gradient squared. This is comparable with exactly the integral of these Gaussian coefficients, okay? So you've actually got some leeway into what you want to write here, but for instance, this this will do the job. So we have this integral, these Gaussian coefficients comparing with this gradient. So if we look back here, right, then essentially what you do is the following: you pick a decent kind of approximation of this curve. Oh, I don't think I'm doing a very good job here. But think of this as like a decent piecewise approximation of this curve, so it's small at every point, which the beta numbers will give you, right? And then we apply, and then what we can do is we can transfer this smallness assumption here, this alpha number condition, to this approximation. Right, so we can transfer that estimate from the curve to its approximation. But then we can use this estimate that tells us that actually that says something about the gradient of that Lipschitz mapping, right? And so you have a gain there that you're getting this better and better approximation of your snowflake. And as you get a better and better approximation, you can say more and more about these alpha numbers based on this property 3. But then the more and more you can say about the alpha numbers, the more control you have over the gradient of this curve. And it turns out that you can play this and you can win, and you end up actually showing that actually the curve has to intersect this a good approximation. As long as the approximation is fine enough, actually the curve has to intersect it at a big place in the measure. Okay, so this is a kind of a nice scheme in geometric measure theory that's been played out a number of times now. And so we in this second half we modify that. Okay, so yeah, but I'm out of time. So thank you very much. Sorry for going over time, and yeah, thanks for having me again.
Ben, thank you very much for for the great talk.